Hello everyone. In this video, we are going to continue our study of a Laplace equation, but in this case, what we are going to do is we are going to see how to solve a Poisson equation with the Dirichlet boundary condition, right? So let's say you have an equation which looks like this: Laplacian of u equals to 0. Yes, and it is if you want to put it this way, let's write it in 2 dimension. F is a function of x and y, and let's say this is in some domain D. Clear? Again, D, we are always going to assume it is a open and connected set. Clear? Connected, if you remember, what is it? You take any 2 points on the set, you can put a continuous function joining those 2 points, which lies entirely on the set. That's what our definition is. Okay, open, of course, you guys know already what is open set. So we have Laplacian u equals to f of x y, and the condition which you want to put is u is essentially nothing but g of x y. This is a different function g of x y on the boundary of this domain, right? So the boundary of this. Clear? As an example, let's just understand this thing. So let's say that I can give you this problem. Let's say I give you this problem: Laplacian of u, yes, equals to something. Yes, let's say sine of x cosine y. Yeah, that is, this is your f of x y in this case. Yeah, and the thing is, it may happen that you are given some boundary data. What is the boundary data in this case? The boundary data is, let's say, I'm saying that it is, let's say, x plus y. Yeah, x plus y on the boundary. So what I'm trying to say is this: on the boundary means if you restrict. So basically, we are looking for a function which is continuously differentiable and also continuous up to the boundary, such that when you restrict u to the boundary itself, then it is x plus y, right? Yes, then it actually matches with the function x plus y, and inside what happens is it should satisfy this particular equation which is given by Laplacian equals to f of sine x times cosine y. I hope this is clear. Okay, so let's do this thing. So this is just an example. I will just give you a general idea of it. So what we want to do is this: we want to find an explicit solution if it is possible. Yes, we'll see what to do. Okay, now let's just assume. Yes, assume. See, what we know from the earlier video, if you remember, that we know how to solve the Laplace equation, right? Laplacian u equals to 0 and u restricted to the boundary, let's say that is equals to some function f, whatever that function is, we don't care right now, some function. Okay, the point is this equation we know, Laplacian u equals to 0. How to solve it? So we somehow, if we can transform the original equation, our equation here, into that sort of equation, then I mean, we have some hope of solving it, right? Okay, so what we do is we assume the solution, okay, can be written in the form, what is the form of the solution? It is basically u equals to v plus w. Clear? And what happens to what is v, what is w? So v is a particular solution of a Poisson equation. So if you remember in OD, what do you do? See, let's say I want to solve this equation: y double prime equals to f. Yeah, in OD. So this is OD. What we do is this: see, let's say if I want to find a general solution of this equation, what do? We find a particular solution of this equation. So let's say yp is a particular solution of this equation, and y, let's say g, yeah, or y naught, let's say, I don't know, maybe yh, let's write it, is solves this equation, y double prime equals to 0. Now you can see that if this happens, then yp plus yh, yeah, so this is the general solution of the homogeneous equation, y double prime equals to 0, and then this is the particular solution of our original equation. So essentially in this case, you can see yp plus yh solves this problem, right? It's a solution of this problem. Yes, so exactly that same sort of thing we want to do. Okay, so what do I do here? One second. Yeah, so we want to put u as a v plus w, right? And such that what happens to the v? V is Laplacian of w. Laplacian of v should be the f, and Laplacian of w should be 0. So we want to divide u, any solution of this problem, let's just call it 1, any solution of 1, into 2 parts, u plus v, right? And what I'm saying is this: v satisfies the harmonic equation Laplace u equals to 0, and W satisfies, sorry, and V satisfies our original equation 1. V is a particular solution of 1. Yeah. Now the point is this, how to find V, that's a different question, but I mean, you understand, huh? I will give you an example of how to solve all this. Okay. So if you have something like this, then you see the solution, then okay, Laplacian of W we have is Laplacian of W equals to 0. Clear? See, W is U minus V essentially. Yes, let me write it here. W is U minus V. Yeah. So Laplacian of W, if you look at, it is Laplacian of U minus V, which is nothing but Laplacian of U minus Laplacian of V. And this is nothing but, you see, this is Laplacian of U is given to be F, and Laplacian of V is given to be F. So that gives you 0. So essentially it means that we have Laplacian of W is equals to 0. Of course, we already had that. We are just that's what we assumed. But the thing is also in D, the domain D, yeah, and also if you restrict W to the boundary of D, clear? What happens if you have that restriction? See, U restricted to the boundary is G, yeah, and V restricted to the boundary. Now, V, we don't know what it is restricted to boundary. So basically, we say that V is a solution which is up to C omega bar. So basically, on the domain, in the boundary also, if you restrict the function till boundary, it remains V. So your W becomes G minus V on the boundary. Okay, so it is G of xy minus V on the boundary. I hope this is clear. Okay, now of course we don't know what W is, but we need to ascertain this. Now how do you find a particular solution of this sort of problem? Yes, let's say that there are, of course, you see, this method does not really work all the time. You have to understand that. But what we can do is, let's say that in this case, yeah, in this case, if you have, let's say, F is a polynomial of degree n plus 2, yeah, and let us just assume, yeah, that F is a polynomial of degree n plus 2. So essentially what I am saying is this, let's say x to the power 4, that sort of thing, y square plus y square, that sort of thing. Yeah. So yes. Now you see, if Laplacian looks like this, so essentially you can think of it. So let me start with a very easy example. See, let's say f double prime looks like x square. Yeah, something x square. It's a one dimension. Think of it as one dimension. F double prime of x is x square. Then you can actually see that f should be a constant kind of thing, right? It should be. Yeah, x square or some constant times x square. So essentially, if you want a polynomial of degree 2, f the second derivative of it, f should be kind of constant. If it's a polynomial of degree 4, it should look like a constant times x square. Clear? Kind of. So what I am trying to say is this, that here you can actually use similar sort of thing, that if so let me put it this way, if f of xy is a polynomial in x and y here, polynomial, okay, of degree n. Okay, if it is a polynomial of degree n, we are basically looking for a solution. So the solution should look like a polynomial, of degree n plus 2, right? Because this is a second order equation. See, if the solution is degree n plus 2, then the second derivatives, you can think of it like 2 degrees less, right? So it should be n. So and that second derivative is nothing but f. So that should be of degree n. So that's the general idea of it. Yeah. Okay. Now all of this is fine. So this is just the theory part. Let me just explain to you how to work out a problem like this. So let's say that we look at this sort of problem. Yes, that Laplacian of u equals to minus 2. Okay, some example doesn't have to be very specific. Let's say 0a cross 0b. You remember when we talked about the harmonic function, we were looking at an equation like this, and the boundary data is given by u of 0y equals to u of ay equals to u of x0. So essentially y equals to 0, and u restricted to y equals to b is 0. So essentially in all the sides of the rectangle we are essentially taking u to be 0, but the Laplace of u is going to be minus 2. That's what our assumption is. Clear? Okay. So this is an example. Sorry, this is an example. Okay. So how do we solve this problem? Yes. So let u equals to v plus w. Again, as I was telling you, it is not always possible to solve this sort of problem explicitly. Yes, in some particular cases we can do this. That's what I'm trying to say. Okay, and those are the cases which you are looking for. So let's look at an easy equation example which looks like this. Okay, now u equals to v plus w. Now here you see what is f. F is essentially minus 2, so it's a constant, right? Now you expect u to have 2 degrees more, the solution. Yes, otherwise if u is like a second order equation, polynomial, then the double derivative of u essentially should be a constant kind of thing, right? That's what we discussed. So that's the idea here. Okay, and v is of the form v of xy equals to a plus bx plus cy plus dx square plus exy plus fy square. Clear? So what is v? As I told you, it should be second degree polynomial, right? Now I am writing this thing. This is the second degree polynomial, the most general form of a second degree polynomial. So this is nothing but the general form of a second degree polynomial. General form of a second degree polynomial. I hope this is clear. Yes. Why am I choosing this thing? Because the derivative, the twice derivative should actually give us constant. That's the general idea of it. Clear? Okay, if you put it in the Poisson equation, so substituting in the equation, we have, okay, see the Laplace, the v is such that it solves this problem, the original problem, Laplacian v equals to f and Laplacian u equals to f. So basically these are the same problems. Yes, v is a particular solution. Yeah, I did not write it. V is a particular solution. Okay, of 1, and w solves Laplacian w equals to 0. So v is a particular solution, so v should solve this equation. So I have to substitute, we have to substitute it here. So what we do is, if we do the substitution, we get 2d plus 2f is equals to minus 2. This is 0, this is 0, this is 0, this second derivative, right, twice derivative, and this twice derivative. If you put everything together, you will see that this is what I wrote is correct, right? Okay. Yes. So now I hope this is clear. Yes. See, let's say v is this. So what is v of x? V of x is nothing but b plus 2 dx plus ey. Clear? And what is vxx? If you do it to vxx, this is gone, this is gone. You are only left out with 2d. And similarly, you are only the other y, with respect to y, you are only left out with 2f. So 2d plus 2f. I hope this is clear. Okay. Now, see, the thing is, I mean, there are different, because there is no other information on d and f. So there can be, I mean, many d and f which satisfy this thing. Clear? So there will imply that if I'm choosing it, let's say equals to minus 1 and f to be 0, this is just a particular solution. Remember, you don't want all the solutions, just a particular solution. So basically, since d and f are arbitrary, you can take df anything and that will satisfy this equation. Absolutely no issues. Okay. So if I'm checking d to be minus 1 and f to be 0, then the particular solution v of xy, So now you understand how to find a particular solution, right? V of xy will look like a times x square minus, sorry, a times x what is, one second, d is minus 1, d is minus 1, so x square minus x square, yes, okay, minus x square. Okay, see, f is 0, yes, d is minus 1, this is minus 1, so basically this term is gone. We only have the other remaining coefficients are arbitrary, right? I mean, they don't have any restriction on it. Clear? So what we are going to do is we are going to choose it in such a way that the v that actually becomes 0 on x equals to 0 and x equals to, so this choice is such that v restricted to x equals to 0 on line and v restricted to x equals to a has to be 0. Yeah, this is what we are choosing. So essentially, you see, we have to have a particular solution of this problem, right? The whole problem. So on the line x equals to 0 and on the line x equals to a, we want v to be 0. Clear? So this is one solution of it, a particular solution. Yes, you can check this thing. Please check this. This is very easy. Yeah, check it. Okay. Now, you see, v is there. Now we have to find w, right? That's the important thing. Now, what does w do? See, now to find w, see, Laplacian of w is equals to 0. Clear? In 0a cross 0b. You remember w is that harmonic part. So essentially we are decomposing the function into two parts. W at the point 0y equals to minus v at the point 0y, which is equals to 0, and w at the point ay, okay, equals to minus v at the point a0, which is equals to 0. Clear? You remember? See, it becomes g minus v, g0 in our case, it is given. See, g0 in our case. Okay, so it is only minus v. Okay, what about w of x0? Let's just see. W of x0 is nothing but minus v of x0. Okay, which is minus, you see, v of x0, v is given like this, so it is minus ax minus x square. Clear? And w of xp is nothing but minus v of x comma b, which is nothing but minus ax minus x square. Is it okay? Right? Now the thing is this, we need to solve this. Now this, of course, I am not going to do it. Yeah, I am going to put it like, let's say this is 1, right, 2. Yeah. How to solve it? Of course, you know what do? You use separation of variable and solve this problem. You can easily do it. And I mean, of course, you have to do some work, but it can be done, of course. Yeah, and I will tell you what the solution is. So essentially, the solution here will look like this. W of xy will be summation n equals to 1 to infinity n cosine h n pi y by a plus bn sine n pi y by a, and then sine of n pi x by a. Is it okay? So this you have to check. Please check it yourself that this is the solution of this problem. This solves this. Okay, this I am not doing this thing because this is essentially the separation of variable thing which we already did. Yes. Okay. Now the thing is this. See, this actually solves everything except these two. Yeah. So we have to put those two conditions here. So let's see. Now, if you put those two conditions, w of x0 is nothing but minus ax minus x square. Clear? And that is nothing but, if you put here y equals to 0 in this equation, y equals to 0, then it becomes n equals to 1 to infinity n sine of n pi x by a. Clear? And w of x comma b, this will look like minus ax minus x square, and that will now be nothing but again y equals to b here, right? So n equals to 1 to infinity, we have to put b here, yes, y equals to b. Okay, so that becomes an cosine hyperbolic n pi b by a plus bn sine hyperbolic n pi b by a, okay, and then sine of n pi x by a, n pi x by a. Clear? Okay. Now, if you, this is in the Fourier series part, right? See, this is Fourier series, Fourier sine series. Yeah, again, this is also Fourier sine series. You can solve it. Yeah, so solving it again, this you have to do it yourself. Please check it. Huh? Do it yourself. Okay. So solving it, what do you have? What is an? An is nothing but 2 by a, Fourier sine series, right? 0 to a x square minus ax. You remember f of x sine of n pi x by a, n pi x by a dx. Fourier sine series, yeah. And of course, if you, look at the solution of this thing, you can do that, and what you get is it is 0 if n is even, and it is going to be minus 8a square by pi cube times n cube if n is odd. Clear? Okay. And so this is from the first equation. What about the second? And what do you get? The second is an cosine hyperbolic n pi b by a plus bn sine hyperbolic n pi b by a, okay, is nothing but 2 by a 0 to a x square minus ax sine n pi x by a dx. Okay. All right. I hope this is okay. Yeah. So, thus, what do you have? Thus, what is your bn in this case? Bn will be, so this bn's, n's we already have, bn's we need to find. So, bn's are 1 minus cosine hyperbolic n pi b by a by sine hyperbolic n pi b by a, okay, times an, of course, times a. Clear? So, now what is the solution of the Dirichlet problem? Yes, then the solution is this. So, if you put everything together, therefore, the solution u of x y, what should it look like? It should look like this. It is a minus x times x, yes, that's your, this function v minus w, right, that w part is there. So, w if you put it there, that 8, that an's are this, right, you see, n is odd. So, essentially it will look like 8 a square by pi cube, and then you have the sum n equals to 1 to infinity sine hyperbolic 2n minus 1 pi b minus y by a plus sine hyperbolic 2n minus 1. So, you remember for n odd we have that this, otherwise it's 0. So, we have to put that part there, that is why I am writing it like 2n minus 1 pi y by a, okay, by sine hyperbolic 2n minus 1 pi b by a times sine of 2n minus 1 pi x by a by 2n minus 1 cube. Okay. So, it is a big expression, but that is how to solve it. Is it okay? Fine. Now, let me give you another form that let us say, what do we know right now? We know how to solve a what sort of equation? Harmonic equation, right? So basically a harmonic function. Laplace equation, if it is given, let's say Laplacian of u equals to 0 is given in some rectangle R, and you have some restriction on the boundary, which is 0. So Dirichlet, or let's say G, Dirichlet. So Dirichlet boundary. You know how to solve it. Separation of variable, yes. Okay. Now let's say Laplacian of u equals to f, that is given. Not all f, of course, but for a certain kind of polynomial kind of f, we know how to solve it. This is how. It is big, but it is solvable. That's what I'm trying to say, right? You need to do some like very tedious calculations, but it's okay. And so u restricted to the boundary is G. Again, this is subject to Dirichlet boundary, right? Now the point is this. Let's say that if we have not the Dirichlet boundary, but the Neumann boundary, what do you do? Okay. So let's look at the second example here. So the Neumann problem. Problem in a rectangle. Okay. How to do this? Again, I am doing everything for a rectangle. You can do it for discs also, or spheres also, or cuboids also, or parallelepipeds also, right? But the point is not parallelepiped, basically cuboid kind of thing, right? Okay. Now, so the point is this. Why? Because the separation of variable works. Clear? Okay. What's Neumann problem? Neumann problem, as you remember, the boundary condition is different. So it is Laplacian of u equals to 0. We want to do it for x between 0 and a, and y between 0 and b. Okay. See, if we know now by the earlier thing, you see this idea which we did, the boundary conditions, here we have used it in such a way that because we know how to solve the Dirichlet problem for the Laplace equation, we exploited that idea. Clear? So here, let's say if we know that how to solve the Neumann problem for the Laplace equation, then we can exploit the exact same idea on the other problem also. You understand? With the, let's say, the same problem with the Neumann boundary, we can use similar sort of idea. Okay. Now, you see, Neumann boundary is essentially we need to have some idea on the derivative of u. So what are these? So let's say ux with respect to x on the line x equals to 0. This is, let's say, f1 of y. Okay. So you have this rectangle. Okay. 0a and 0b. Yeah. On x equals to 0, you have, this is f1. This is ux is f1, not u. Okay. Now, the second condition is ux with respect to ay. So this is for 0 less than y less than b. Less than equals to boundary, right? Okay. So ux at the point ay is f2 of y. Again, 0 less than y less than b. Okay. So here this is x is equals to a, right? So x equals to a, this line x equals to a. So here also ux is given to be f2. Clear? Okay. Now uy at the point x0. x0 is y equals to 0 line. Where is y equals to 0 line? This one, right? This one, right? Y equals to 0. So ux equals to f3, and here we'll put ux equals to f4. Okay. So uy at the point x0 is, let's say, g1 of x. You see, this is a function of y, this is a function of x, right? And this x lies between 0 and a. And similarly, uy at the point, one second here, x and what is this, b, right? This is g2 of x. Clear? This is g2 of x. So this is again x is between 0 and a. So slightly different conditions here, and this is called Neumann condition. So please remember, the data is given with respect to x and with respect to y variables. Clear? Okay. Now you remember the Neumann condition. There is a compatibility condition here. Integral of the f is equals to going to be 0. So the whatever is on the boundary data. So the compatibility condition. that must be fulfilled will look like this. Fulfilled, okay, is okay. So how the compatibility is essentially, you see why this compatibility condition is there. It's essentially due to the fact that if you use separation of if you use change of variable for what is it, integration by parts formula, you see that this compatibility condition is an essential tool, otherwise the whole thing won't work. Okay, so it is 0 to a g1 of x minus g2 of x dx plus 0 to b f1 of y minus f2 of y dy is 0. You remember the compatibility condition, integral of the boundary data is going to be 0. So that's just the thing, we just writing it like this. Okay. So now the solution of it, how do you find the solution? Yes. Okay. What do you do? So let's say that we assume that u of xy, okay, is nothing but u1 of xy plus u2 of xy. Again, similar sort of thing. So we want to break it up, u2 of xy, decomposition, where u1 of xy satisfies this equation. u1 of xy satisfies Laplacian of u1 is 0, this equation, and u1, okay, how do I put it? Maybe I can write it like this. u1 with respect to x at x equals to 0 line is 0. u1 with respect to x at x equals to a line, so that is going to be 0. u1 with respect to y and at the point x, y equals to 0, that is 0. Sorry, g1, g1. These conditions I want to interpret. So essentially what I am doing is this 4 boundary conditions are there. On the 4 of the boundaries it is non-zero, right? So we are breaking it up, you understand? So ux I am taking it to be 0 0 initially, u with respect to x, and the thing is the other part we am putting the boundary condition, which is g1 of x and del u 1 del y at the point xb, this is g2 of x. Clear? So this is one condition. You understand what I am doing? The boundary condition we are breaking up. See, if u equals to u1 plus u2, if you are defining u to be this, then Laplacian of u is Laplacian of u1 plus Laplacian of u2. Laplacian of u1 is 0, Laplacian of u2 is 0, right? So this is actually giving you 0. See? Okay. And what about the boundary condition? Boundary u1 in these two is g1 and g2, and these two it is 0. Again, u2 will choose it in such a way that in these two it is f1 and f2, here it is 0. So if you add all this thing up, what happens is v will satisfy this problem. Let's just call it 3. Clear? That's the idea. We're just breaking up the boundary in such a way. Okay. And what does u2 do? u2 satisfies, u2 of xy actually, it satisfies Laplacian of u2 is 0, del u2 with respect to del x at the point 0 y, this is f1 of y, del u2 with respect to del x at the point ay is f2 of y. You see, this 2 we are putting, and the next 2 we will put it as 0, del 2 of del y with respect to x equals to 0, x0, this is 0, and del u2 by del y at the point y equals to b, this is 0. Clear? We are just breaking up in such a way. Now of course this is again Neumann problem. You see, let's call it 4, let's call this 5. 4 and 5 are again Neumann problem. So there is a compatibility condition. Yeah, let me write it down. The compatibility condition. I will just write it like this. Compatibility condition will look like this: 0 to a g1 of x minus g2 of x dx is 0, right? and from the second equation 0 to b f1 of y minus f2 of y dy is equals to 0. It's okay. Those are the compatibility conditions. Now, you see, if you can find u1 and u2 solving 4 and 5, we actually have a solution. Clear? Okay. So, now this is the tricky part. How do you solve, how do you find something like this? Yes. Now, this problem, what I want you to do is, I will give you some idea how to solve this, and I want you to do it yourself, okay? Because there is a lot of calculation which needs to be done, and I will just give you an idea. So what we do is this. So this is, we want to find a general solution. General solution. Okay, that's the idea. So we want to find this general solution. Okay, so there is this mathematician whose name was Grunberg. Okay, so what he did is he proposed that they look for a solution like this. So we look for a solution like this, u of xy, okay, which is nothing but capital Y naught. This is some function, yes, nothing special about it, of y, clear, plus summation n equals to 1 to infinity xn of x yn of y. Okay, see again, there is nothing special about this sort of thing what he did. Essentially what the idea here is this. So let me give you a simple idea. Let's say that for a OD, yes, y double prime equals to f. I want to solve this OD. What do you do is essentially, if there is a solution, let's say y, there is this function, right? So let's, if you want, you can just put it in terms of a y of x. You can write it in terms of a Fourier series, right, which is given by a naught plus, you can write it to be a naught by 2. That is what this 2 is, plus summation n cosine nx plus bn sin nx, right? Plus bn sin nx. We can write it like this, right? Now you see what is happening here is this. Let's just call this thing. This is some function of x. Clear? So this is nothing but a constant. Forget about this thing. Let's write it as a naught. Okay, some constant a naught. Okay, plus summation xn and n equals to 1 to infinity. Of course, some constants, constant times. See, these constants are there. Let's just say the constants are cn. Cn times xn, summation n equals. Now the thing is, this function is just a function of x. Yes. Now let's just try it to be. So I am looking for a function of x and y. Yeah. So let's say if you want to change it to a function of x and y, this constant will change to a function of y. So for a fixed y, so let's say, let's not write it as y, you will get confused. Let's just call it phi. Any solution of this problem, phi double prime equals to, will look like this. Now you see, if you fix a y, let's say this is your solution. Now if you let the y to move around, then it becomes u of xy is this constant will not be a constant anymore. It is basically a function of y, right? Yeah, plus summation n equals to 1 to infinity. You see, this constants again will depend on y. So essentially that will be functions of y. So xn is a function of x and yn will be a function of y. You understand? That's the idea. Okay. So this is what we are just writing it here, and this, see, this y naught by a, y naught, if you want you can put it to be by 2. If you want, you do not put it, absolutely no issues here. Okay, this is via the Fourier series. The idea of the Fourier series we are just exploiting here in a different way. Okay, see, what are xn of x now? Here xn of x, okay, this is given by cosine of n pi x by a. Okay, this is an eigenfunction okay, of the eigenvalue problem x double prime plus lambda x equals to 0 and x prime 0 equals to x prime at a equals to 0. Is it okay? So we assume that u looks like this, where this is the xn. Yeah, this is our assumption, and this is corresponding to, so eigenvalue problem, this, which corresponds to lambda n's, which are n pi x by a square, n in z. Clear? So now you see, if you put it in this equation, yeah, this particular thing, you see, if this is your xn's, right? So what we are doing is this xn's, we are explicitly writing down what xn's are. How do you get these two conditions? We get it like this. See, this equation, these two equation with respect to x. So in the, if you fix a y with respect to x variable, the change in u1 is 0. With respect to you see, if you fix a see, x equals to 0 also it is 0, x equals to a also it is going to be 0. So with respect to x, in the x direction. So that is why this is just a function of x. So in the x direction, at the line x equals to 0 and at the point x equals to a, this is 0. So that's why we need this boundary condition. Okay. So and this we are just choosing it in this way. We are choosing that, let's say that x is satisfy the eigenvalue problem. Okay. And how are you getting the boundary condition? Boundary condition we are getting because of these two conditions. We are exploiting these two conditions. Clear? So it's a little tricky, but that's just the way of it. Okay. So now you see, if you put it in the equation, what do you get? You get yn of y, that will be 2 by a, 0 to a Fourier series, yeah, you remember, u of xy, okay, and then xn of x dx. Clear? And if you write it properly, it is 2 by a, 0 to a, u of xy, and then cosine n pi x by a dx. Okay. So now you see, if you have the original equation, right, the first equation, Laplace u equals to 0, yeah. So you see, if we are multiplying the both equations, so that equation with, so multiplying Laplacian of u equals to 0, okay, by this 2 cosine n pi x by a, okay, and integrating with respect to x, okay, from a to b. Of course, we obtain 2 by a, and then 0 to a, uxx plus uyy cosine of n pi x by a, okay, dx is equals to 0. Clear? We are just multiplying it by equation. See, Laplacian of u equals to 0, that is given to us. Yes, so we are just multiplying it by cosine nx, that cosine part, and then integrating it. That's the thing. So that will imply that essentially what is it? This is yn double prime plus 2 by a, 0 to a, uxx cosine n pi x by a dx. This is 0. Is it okay? This is 0. Okay. And you see, if you integrate the second term by parts, okay, so essentially this is this part, if you integrate it by parts, what do you get? And integrating, we get yn double prime of y minus n pi by a square yn of y. This is fn of y. Okay, so I really need you to check this part. Please check this thing. So this is integrating the second part. Yeah, so please check this part. Yeah, this is a very big calculation. It's not possible to work out every little details of this thing. Yes, so but you have to do it yourself if you want to learn. So integrating this, you get this. Okay, and where fny is 2 times f1 of y minus 1 power n f2 of y by a. Okay. Okay. So this is what? This is nothing but a ODE, right? This is an ODE. So you can solve this ODE. Yes, if you solve it, you get a solution which is rather big, but let me write it down. We get yn of y is nothing but an cosine hyperbolic n pi y by a plus bn sine hyperbolic n pi y by a, okay, plus 2 by pi n pi a, essentially 0 to y fn of tau sine hyperbolic n pi by a y minus tau, okay, d tau. Clear? So, and how do you find what ans and bns are? Ans and bns and are like this. You see, yn prime of 0 is nothing but 2 by a 0 to a, right, uy with respect to x0 cosine n pi x by a dx, okay, and which is 2 by a 0 to a, and then you have what is it? Yeah, g1, right? It is g1 of x cosine n pi x by a dx, okay, and yn prime of b, if you put it, then that is nothing but again the boundary conditions, right? It is 0 to a g2 of x and then cosine n pi x by a dx, okay, right. So if you put n equals to 0, of course you can see that, so for n equals to 0, essentially for n equals to 0, you have the equation which looks like this: y naught double prime of y is nothing but 2 by a. So I am taking it to be by 2. The solution I am taking it to be half. Okay. So it is 2 by a 0 to y, and then f1 of tau minus f2 of tau d tau plus a constant c. Clear? Okay. So there are big conditions. Now if you put this to this particular thing here, you see, yeah, this boundary condition here, what do you get? You get that the c, and so this condition, this boundary condition, therefore you get c is nothing but 2 by a 0 to a g1 of x dx. Clear? Okay. So therefore what is u naught y naught prime? Therefore y naught prime of y is 2 by a and then 0 to y f1 of tau minus f2 of tau d tau plus 0 to a g1 of x dx. Clear? So therefore y naught prime at the point b, if you want to consider it, becomes 2 by a and then 0 to b, y becomes b, f1 of tau minus f2 of tau, okay, d tau plus 0 to a g1 of x dx, okay, right. Okay, also from this equation, yes, okay, this is becoming very big, but let me just do it. From this equation also, y naught prime of 0, you see, y naught prime of 0 is this particular thing, right? So essentially if you equate those two, what do you have? Y naught prime of b is nothing but 2 by a 0 to a g2 of x dx, right? So if you put all these two expressions of y naught prime b, so you have this and you have this, so if you put everything together you get 0 to b f1 of y minus f2 of y dy plus 0 to a. If we put everything together g1 of x minus g2 of x dx equals to 0. Okay, so this is necessary condition for the existence, the compatibility condition. Is it okay? So this is how we do it. So essentially what we do is we do a lot of calculations. Essentially we break the problems into two part, one part and another part, and after that once you have this once you have this equation, Laplace you know you can use separation of variable, and this data this boundary data, what you do is you can use this sort of idea that the general solution will look like this, and then you solve the problem using that what xn is, which is a solution of this problems, and then try to find what yns are. Once you find it, you put it together and then you have your solution. Yes, so this is a little tricky, it's very big, but this is how we solve it. It is not always possible to solve it, but in some particular cases we can do it. Yes, maybe you can do one problem corresponding to this, and you learn something. Okay, so with this we are going to end this video. Thank you.